All right. Hi, everybody. Welcome to our Math 60 lecture. Hold on. Let me pause the recording while I turn on the projector and resume. All right. Our video lecture today is section 4.4 and maybe a little 4.5, as we'll probably have time. Section 4.4 is modeling situations with mathematics, specifically with algebra. So good news is the situations we're going to be modeling are going to be very simple from an algebraic standpoint. The algebra will be simple. No like fraction reduction, no addition of fractions, things like that. We are going to be focusing on this idea of changing our representations of mathematics. I know I mentioned this, but it's probably been a while. There are four main representations of mathematics. Symbols, that's what we've been working with the most. Numbers, we've been working with those a lot as well, especially with arithmetic. Pictures and words, we haven't worked with a whole lot yet. And that's basically what the second, this last portion of the class is about. It's going to be about the words and the pictures. So we're going to be focused on moving from words to pictures in this specific section. And that's really, oh, sorry, not pictures, sorry. From words to symbols. And that's really what modeling with mathematics is. It's moving from questions that you might actually encounter, which are usually in the form of words, whether written or spoken, to mathematical symbols so that we can use our mathematical tools. It doesn't mean we have to go straight from words to symbols. Sometimes taking our words and figuring out some numbers that fit them help. Or drawing a picture of the situation can also help. But ultimately, when we're modeling, we usually want to end up with symbols. So let me just give you an example. This is going to be a tough lecture for me because since it's words, it's going to involve a lot of writing and my hand might start cramping, but that's okay. Suppose I want to buy a Thanksgiving turkey. The turkey costs, let's keep it kind of simple, 0.04 or $0.4 per pound. So 40% per pound. It's been a while since I bought a turkey, at least a year. So I don't know if that's right. I think it's close. Yeah. I want to spend less than $5. How heavy or how many pounds, how heavy of a turkey can I buy? So yeah, I don't like that $5. I think that's, nobody spends $5 on a turkey. Bad example. I'm still going to do it. How heavy of a turkey can I buy to spend exactly $5? Now, if you want to model this with symbols, the first step is to choose some variables so that I can do algebra. And here, probably what I want to choose is, I like to always use X when I can. Often books, often different people use different letters that maybe match the word that I'm modeling. Maybe T for turkey or P for pound. But as long as you're defining it, you can pick any letter. And I like the consistency of choosing X when I can. Let X be the number of pounds a turkey weighs. This is a good definition because I'm specifying X is a variable that represents a number. And so far, X is unknown, just like the weight of the turkey is unknown. So a good definition with a variable is a variable, it needs to represent a number, because everything we've been doing with algebra, even when it's variables, they've been numbers. And there's not much point in picking a variable if there's something that we already know. So let me write down a couple bad definitions, or less useful. Here's a straightforward bad definition. Let X be turkey. Turkey is not a number, right? I don't number the turkey. What I'm caring about is the weight of the turkey in pounds, right? This is not a number. A useless definition would be let P be the price per pound of a turkey. Can I get this all on the thing? Why is this a useless definition? If anybody online wants to chime in with the chat or unmuting, they can, but I'm not going to put that on you. It's Monday. We got some sleepy faces, including mine. This is a useless variable definition because it's not unknown. I already know it's $40 per pound. It's not that it's wrong, it's just not helpful. I already know the price per pound. Why am I going to replace a number with a variable if I already know the number? It's just going to make my work harder. It would also be useless to say, let D equal the amount of dollars I have. Let D be the number of dollars. All right, that's not very useful because I know I have $5. So let's take our good definition, which is a variable that represents a number and something that we don't know yet, and see if we can figure out a way to model this situation. So if we want to, oh, I never used this page. Oh, I started that. If we want to model this situation, we want to use symbols to explain the relationship. But I really want to emphasize the point that using numbers and pictures can help get us to symbols if we're feeling stuck. So instead, let's start with a numbers representation in the form of the table. X equals the pounds of turkey, right? The number of pounds of turkey. And I'm going to figure out the price I pay for each pound of turkey. If my turkey weighs 1 pound and it's 40 cents a pound, I'm going to spend 40 cents. If it weighs 2 pounds, I'm going to spend 80 cents. If it's weighs 3 pounds, I'm going to spend $1.20. And I notice, oh, this is 0.4 times X, right? It's the price per pound times the number of pounds. Price per pound times the pounds. Because 80.8 is 0.4 times 2, and 1.2 is 0.4 times 3. Let me do a little intuition check. If I have a 10-pound turkey, that should be 0.4 times 10. So that should be $4. And so I see that my relationship is the price I pay equals the price per pound times the number of pounds. And now I fill in the information that I have. The price I want to pay is $5. The price per pound is $0.4 per pound. No point in using variables for these because I know those numbers. And the pounds of turkey, that's what I don't know, that's the X. And so now I have my symbolic representation. I have modeled this situation. And now I say, how many pounds should the turkey be? In a mathematical sense, I want to solve for X. So I'm going to solve my equation. 5 equals 0.4x for x. We don't use decimals a lot in this class, but a decimal is a number just like any other number. So I can divide. Here, let me do that on the next slide. I can divide both sides by that number, which cancels out the 0.4. And then my calculator can tell me what 5 divided by 0.4 is. It's Monday. I haven't woken up my arithmetic brain yet. 12.5. So X is 12.5. But now I want to go back to the situation and put my solution in context. I can buy a 12.5 pound turkey and spend only $5. And I can guarantee you next time I teach this class, I'm gonna think harder about what the price per pound should be, because that would be nice, but I don't think that's how that works. All right. So let me write down the general steps. For modeling a situation with algebra and solving. Solving the situation, that's a little strange to say, but that's what it is. So step one, read the question carefully. Read it twice if you need to. And in particular, look for the numbers and the unknown quantities. The ones that actually matter. I'll give you an example of something that where there are numbers in the question, but those numbers don't actually matter when we model it. Step two is define the unknown quantities. Often there's just one, sometimes there's more than one, as variables. These variables must represent numbers. Pounds of turkeys, number of days, step three, build an algebraic equation or expression, usually equation, to represent the situation. Use a table or pictures if it helps. We'll do one where maybe drawing a picture is going to help. And then step four, solve the algebraic equation. Let me add in step two, I usually use X, but you're going to see a lot of different letters. Okay, solve the algebraic equation for the unknown variable. i.e. X. Always a good idea to check your work. And you can do this numerically or kind of just a gut check. And then step five, write your answer in the context of the situation. because that's ultimately the goal. The goal ultimately is not to say X equals 12.5. The goal is to walk into a grocery store and buy a 12.5 pound turkey. You all can write those down. That's going to give me a little time to think of an example where a picture would be helpful. All right. So let's take another look, or let's take a look at another example. Let's see. I need to rent a car. It costs $20 per day to rent. And I pay $3 for every 10 miles that I drive. If I rent the car for 5 days, how far can I drive it to keep the total cost below $160? All right, so let's approach this with our steps. We're gonna read the question carefully, looking for numbers and the unknown quantities. So as you're writing it down, I noticed some of you are writing this down, that counts as reading it carefully. Right? When you write something down and you check and you make sure you get all the words, that's a good way to read it carefully. In fact, if you struggle with the reading carefully piece and the question itself is not too long, write the whole question again. It's a good way to make sure you're actually reading it carefully. So step one, let me just note some numbers. We got 5 days, $20 per day, $3 per mile, total of $160. And my unknown quantity is how far can I drive? And so step two will be to set a variable. Let X equals the number of miles I drive. I gave up on trying to figure out a good picture. There are other questions that really benefit from pictures, but they just don't tend to be the type of situations that we're modeling in this class. So We'll get to those in the future. But I am going to use a table. I want an algebraic representation. But I'm going to start with a table. X is a number of miles I drove, and then here I'll put the total cost. So suppose I rent that car. I have it for 5 days, and I don't drive it anywhere. How much is my total cost going to be? Well, it's $20 per day. So even if I don't drive it anywhere, I'm still going to spend $100, which is 20 times 5. And now I start driving. Let's suppose I drive for 10 miles. Well, that means I'm going to have the $100 plus the $3 for the 10 miles. And if I drive for 20 miles, it's going to be the $100 plus the $3 for the first 10 and the $3 for the second 10. And there would be absolutely nothing wrong with solving this question using a table. Using a table is making a reasonable guess and checking systematically. And I could see pretty quickly that sticking to like 10, 20, or 30 is not going to get me there. So I could jump up a lot. Maybe let's try 100 miles. So if I drove 100 miles, that'd be 100 plus 3 times 10, right? Because that's 10 sets of 10, which is 130, and I'm still below. But by building this table, I can see it's going to be 100 plus 3.3x. $100 plus 30 cents per mile. Or I could think of it as $100 plus 3 over 10 times x. And there I see my $3 per 10 miles. And now I have my algebraic representation. My total cost should equal $100 base cost plus 3/10 times the number of miles. That's step 3. Step 4, let's solve it. I wanted to spend no more than $160. So 160 should equal 100 plus 3/10 x. And I solve for x. So I'll start by subtracting 100 from both sides. And I get 60 equals 3/10 x. And to isolate x, I need to divide by 3/10, or using our fraction skills, multiply by the reciprocal times 10 over 3. And I get 600 over 3, or 200, equals x. So I'm saying I can drive 200 miles to keep my cost below 160. And I'll do a quick check. I'll do a gut check. Looking at my table, something in the 20 to 30 range is way too low. Even $100 is a little bit too low. So getting a number more than 100 makes sense. But if I got like 2000, that probably would be too big. So I'm satisfied. I said, you know, I don't think I made any big errors in my arithmetic, and the number I got is reasonable. I'm gonna stick with that. I'm gonna squeeze step 5 here, just so it all fits on one page. Write your answer in the context of the situation. I can drive 200 miles in 5 days to spend $160. Okay. These examples take a longer time, which is why I don't do as many of them. I'm going to do a couple examples from 4.5, but 4.5 homework itself is an extra credit. And here in 4.5, we're going to be solving equations where the variable shows up more than once. As a review, if I have 3x plus 7 equals 34, right? My variable is showing up one time. And if I want to solve for x, I do something very similar to what I did in the last example. Subtract 7 from both sides. I get 3x equals 27. Divide both sides by 3. And I get x equals 9. Well, what if I have x's showing up more than once? What if I have 3x minus 5 equals x plus 15? If you have to solve for x, the first thing you do is you collect like terms, which specifically really means collect all the x's. They're on both sides of the equation right now. So what I'm going to do is I'm going to subtract x from the right side, which means I also subtract it from the left side. And I have 3x minus 5 equals 15. And I collect the like terms. I get 2x minus 5 equals 15. And now I'm back to the previous type of example. Now there's only one x, and I solve it using my tools. Add 5 to both sides. 2x equals 20. Divide both sides by 2, and x equals 10. I can check my work. One nice way to check your work is to use kind of a side-by-side comparison. It's not really a table, but I simply put one side of my equation on one side and the other on the other. And then I plug in my value that I found for x. So I do x equals 10. So I have 3 times 10 minus 5 on the left, and then 10 plus 15 on the right. And I work through the arithmetic. 3 times 10 is 30. 10 plus 15 is 25 on the right side. And then 30 minus 5 is 25. I get 25 on both sides, and that means I got it right. Okay. One more example. We talked about the distributive property last week.